Howdy, welcome to today's computer graphics, animation, and simulation, and today we're going to talk a little bit about springs. In particular, we're going to talk a little bit about spring math, a massless spring damper, a springless mass damper, a damperless spring mass, and a spring mass damper. Basically, a lot of different combinations. So springs are useful for a lot of different things. One of the things we will be covering in the class are damped springy connectors, and this kind of goes along with deformable springy meshes, so we might want to investigate how those work in particular. And so we basically have this model where we have some point of attachment, and this point of attachment has both a spring, which we use a squiggly line, with the spring coefficient, which we call K, and this is connected to some kind of mass. So we'll just do some kind of ball, which has a mass of M. And lastly, we have this damper. So we have this device here that's designed to help take energy out of the spring. And we would like to find out what is the position of the mass along this spring. So there's a couple of forces at work here. The first one we'll call Fk, and this should be familiar to any physics student. We have minus Kx. And then we also have a damper whose force is minus dv, where v is the velocity and d is a constant. So these two are working in conjunction with each other. Okay, so now we would like to see what forces are applied. Okay, so we know that force equals F equals ma. So we will have Newton's second law at work here. So we'll have ma equals some external force plus the force of the spring plus the damper force. And essentially what we want to do is, this is going to turn into a second order linear differential equation. In other words, we will need to rewrite this so that it makes more sense. So we'll have that m times the second derivative of x, which is acceleration, equals our external force minus kx, which is our spring, minus d times x prime, which is the velocity. And this is going to turn into a differential equation here. So we could say that m x double prime plus d x prime plus kx equals some external force. And if we set the external force to 0, then we get what's called the homogeneous form of the equation. Okay? So x double prime plus d x prime plus kx equals 0. And then one of the things that we'll do is we'll set some initial conditions. So those initial conditions will say that x will equal x naught and the velocity will equal v naught. And what will happen is that the equation will then describe how the system will behave over time, especially if it's not disturbed by any outside forces. So let's go ahead and look at the first one, which is the massless spring damper. So we have a massless spring damper, which means that our velocity can be written minus k over d times x. And now if we solve this, and of course I won't tell you how to solve it because we're using differential equations here, but we get the equation x of t equals x naught, which is our initial condition, times e to minus k over d times t. And this is going to yield an exponential decay. So if we were to graph this out, we might start off at 1, and what will happen, as you can guess from the e function, and this is our x-axis, this is our t-axis, is that what will happen is that this equation will decay over time. So that is our massless spring damper, and this comes from the fact that we set m equal to 0 in order to solve our equation. So now let's look what happens if we have a springless mass damper. So in this case, we're going to set the stiffness of the spring, k, equal to 0. And what will end up happening is we will get that our acceleration is equal to minus d over m times our velocity. And so if we do that and we solve this equation, then we will get a equation for velocity where we have our initial velocity times e to minus d over m times t. And the idea here is that we will have a time constant, and this applies to the one, the massless spring damper, but we will get this to be m over d, okay? And for the one we talked about before, I forgot to put it on the previous slide, is that one is d over k. So we can kind of compare the two. And this one also, as you can imagine, will have an exponential decay. So if this is velocity on this graph and t on this graph, then we will have this exponential fall off. Now, what that means is that we can integrate this equation with respect to time in order to get our position. So we will have x of t equals our initial position plus our velocity, initial velocity, times m over d times 1 minus e to the minus d over mt. So just using some old-fashioned integration, we can then find out what happens to this combination. And we would get something similar. This is value for 1. Value for 1. We would get something like a leveling off of essentially of the where the damper is basically gonna we're going to slow the position down, in other words. So if the mass had any kind of movement, then we will see it eventually slow down. Okay? So essentially, if we want to quickly bring a mass to a rest, then we have to either decrease the mass, or we have to increase the damping constant d. Okay? And since the time constant is a ratio, then it's going to basically be dependent on the mass and the damping strength. And in the previous case, it was dependent on the damping strength and the spring constant. There was no mass, didn't have any effect there. Okay, so next we want to take a look at the case where we have a damperless spring mass. So in this case, we're going to set the damping constant equal to 0. So d equals 0, and this is going to give us that acceleration equals minus k over x times, k over m times our x position. And then when we solve this one, we'll have, instead of having to do an extra integration step, we can just go straight to the position. So we'll have some constant c, which is the amplitude, times cosine of the square root of k over m times t plus phi. And phi is going to be essentially the phase of the spring, and what we're going to end up getting, as you can imagine, is, because we have the cosine, so we got x and t, but essentially what we're going to have is just that cyclical motion of the cosine. Okay, this is minus 1 here, and in order to calculate these positions, we have that phi equals minus inverse tan of the square root of m over k times our initial velocity over our initial position, and our constant c, which is our amplitude, will equal the square root of our initial position squared plus m over k times our initial velocity squared. And basically we're just going to have a strut that has a little bit, it has very little damping. Basically it's just going to oscillate with a sinusoidal pattern. Okay, so we can see the cosine here. Alright, so now we're going to put all this together. So we've seen the massless, so a spring damper without any kind of mass, a spring mass damper without a spring. Now we have the spring mass without the damper, and now we're going to stick everything together. So the idea here is that we kind of have an idea that our strut is going to have some kind of oscillation in it, but it should decay over time in some exponential way. And so in order to do that, we're going to take our homogeneous equation and divide it by m. So we'll have x double prime plus d over m times the velocity, or x prime, plus k over m times just equal to 0, and that's going to allow us to get the frequency. So the frequency omega n equals the square root of k over m, and the period is going to equal 2 pi times square root of m over k. Now, we're going to have a damping factor, which we will call z, or xi. So This is kind of a funny looking one to draw, but this is going to equal d over 2 root k times m. Okay, and so we're going to do a little bit of math, but I'm just going to give you the final equation here, which we're going to get x of t equals the exponent, so minus z times omega n times t times the cosine of our omega n, so that's our frequency, times the square root 1 minus z squared times t plus our phase function. Okay, and so we're going to ignore the phase for right now when I graph it, but essentially what's going to happen is that we will then get the case where we're oscillating between, say, -1 and 1. This is our x position, and we got t, so we basically have an oscillation here, but it's kind of going out. All right, and this is going to be very valuable here, and the idea here is that if our damping factor is high, then the time constant will be small, and that means the oscillation will die out quickly. And then if the damping factor is larger, then the frequency basically will decrease significantly below what we would think the natural frequency is. So this has to be less than 1, though, because then so the reason why this has to be less than 1, because you'll see the square root 1 minus z squared, and so therefore the equation will no longer be valid because it'll be negative. And so in this case, essentially when the damping factor becomes large, then the motion is damped out before any oscillation takes place. Okay, and so when this is 0, then we'll call it undamped, and when it's between 0 and 1, then it's called underdamped, and when it's equal to 1, then it's called critically damped, and when it goes greater than 1, then it's overdamped. In other words, you'll never get an oscillation out of it, which makes sense. Then you just get the decay of the motion. Okay, so just by way of review, today we talked about spring math. In particular, we looked at this case where we have a damper, a spring, and a mass. Then we talked about the different combinations you can have. So if we set the mass equal to 0, if we set the spring equal to, if we got rid of the spring, if we got rid of the damper, and then finally if we combined everything all together. So anyways, just want to say thank you, and adios.